Bunun için uygun bir ortamda değil misin? Okey. Hazırız sana. Hoş geldiniz arkadaşlar. Sıradaki konuşmacımız Hamdi Kayaslan. İzmir Yüksek Teknoloji Enstitüsü'nden bir doktora öğrencisi. Birinci sınıfını tamamlamış. Konuşmamızın başlığı da Chain Complexes and Their Homology. Şimdi sözü Hamdi hocamıza bırakıyorum. Buyurun hocam.
Thank you, Uğur. Welcome, everyone. I'm Hamdi, as Uğur mentioned, from Izmir Institute of Technology. Today's subject is chain complexes and their homology. So we are going to build a maybe new concept for some of you, the chain complexes, but from the very basic ingredients of algebra. And we'll try to demonstrate one of the uses of it, homology, through homology. So we first take a look at groups, group homomorphisms, and additionally, for our example, it will be useful, free abelian groups. And then in the second part, we are going to build chain complexes, what they are and what exactness means and what kind of maps we can define between them. And there will be a nice puzzle diagram chasing here. We are going to see an example of it and further examples, but we are not going to solve each of them. I think the time will not be enough. And then we'll move to homology groups of a chain complex, a way of obtaining information, meaningful information from these chain complexes. So a group consists of a non-empty set, usually denoted by G, and the binary operation from G times G to G, where this operation satisfies some set of conditions, which is first one is this operation should be associative, and this operation should have identity element and inverse element. In some sources, you can see that there's a closure property here, but if we start with a binary operation where it is from G times G to G, the closure property is already satisfied, so it is going to be enough to move on with these three properties, conditions, let's say. And if in addition we have a commutativity condition, if this is satisfied also, we have an abelian group. So associativity means, when we take three elements, it doesn't matter in which order we operate them, we are still going to be landing on the same elements. And the identity element means if we operate it from the right side or the left side with any element in G, we are going to be having the element itself, right? So it does not, it does not have any effect on it. So inverse element is the element which gives the identity element when operated with this element from left or right, doesn't matter. And the commutativity is we can just change the order of the elements. We are still going to be having the same element as a result. So the basic examples are we can take the integers, we can take the rationals or reals, and we can take the usual addition on them. And we can just show that these form groups, actually abelian groups under this operation. And we can change the elements. We can have a little bit more interesting sets, matrices. M by M matrices with matrix addition also forms a group, actually commutative abelian group. And M by N invertible matrices forms a group under multiplication, but this is not abelian. When we change the order, we take different results, right? And a little bit more interesting, we can pick a non-empty set X, and we can take the bijective maps, which is one-to-one and onto maps from X to itself. And under the composition, we see that these elements forms a group too. So there are way more examples than these, but these are a little bit basic examples, I believe. So in algebra, when we form a structure in general, a group structure, module structure, ring structure, we are usually interested in substructures too, right? So we are dealing with groups here, and of course the substructure is called subgroup. So what is a subgroup? A subgroup of a group G is a subset which forms a group structure again under the same operation on G, basically. Intuitively, we can say that. And we have a few equivalent ways of checking if a subset is a subgroup or not. But generally, this subset should be satisfying these conditions where it should, of course, contain the identity of this operation on G, right? and it has to have the closure property, and for any element in H, the inverse should be also in H. As I said, there are a few more equivalent conditions where we can check this. And as an example, we can take integers with addition, and the set of all integer multiples of 3 forms a subgroup. We denote it by 3Z. Okay, this set is obviously closed under addition, and for any element in it, the negative of that element is inverse, right? So of course it has 0, as 0 is a multiple of 3. So every condition here is satisfied. This is a subgroup of Z. In general, we can take any integer n, and all integer multiples of this n will form a subgroup nz. And when we talk about subgroups, we can then talk about cosets too. What is a coset? A coset basically formed in the following way. We take an element in G, X in this situation, and we use the operation with every element of H, and we form this set here. Actually, I can use this one, right? Yeah. And this is, called a left coset. And the right coset is defined similarly, right? Now X is on the right side here. So we denote this set, the set that formed by these elements, these left cosets, by G quotient H. This is just a set now, but we are going to give a richer structure to it in a second. Let's see. Here we have an example. We have integers under addition and the subgroup of 3Z, right? So in this case, the left cosets are, we pick elements from Z and we just add them to 3Z. I mean, we denote it like this. So if we pick 0 here, this is the left coset we derive, and 1 plus 3Z, 2 plus 3Z, and when we move to 3 plus 3Z, we can see that this is actually the same left coset with this one. I mean, one is formed like this, right? 0, 3, and all. And the other one is actually the same because, if we add 3 to -6, we form this element. If we add 3 to -3, we form this one. And it is like a shift, but still the overall set is the same. So these are 0 plus 3Z and 3 plus 3Z are the same. And 4 plus 3Z is the same as 1 plus 3Z. So the idea here is we have the same cosets, but with the different elements representing them. Okay, so one remark which is very important: if we pick this element X from particularly from H, then the left coset formed by this X and the right coset formed by this X is going to be equal to H itself. Actually, they are equivalent. If we have this situation, then X is a member of H. Okay, next we have normal subgroups, a special kind of subgroups. In these subgroups, we pick any element from G and we form this set GH, G inverse, which contains elements like this. We pick any element H and we operate it this way. And this this new set should be included in the H. That is the condition. If this is satisfied for every element in G, then we call this subgroup a normal subgroup. Or again, we have the equivalent condition here, which is for every element in G, the left coset formed by this element G and the right coset should be equal. If one of these are satisfied, we can call this subgroup a normal subgroup. And if we have an abelian group where we can change the order of elements, we have commutativity, we can see that both conditions are satisfied because G star H star G inverse is going to be equal to this one because we can change the order of these elements, right? So here we will have the identity, and identity operated with this H will be H contained in H. So this new set is contained in H. And from here we can see that we can change the order of this G and H. We still have the left coset being equal to right coset. So every subgroup of an abelian group is normal. Next, we will be using quotient groups in our definitions later. That's why let's look at them. So when we have a subgroup, normal subgroup in particular here, then we can give a richer structure to this G quotient H left cosets, the set formed by these left cosets, right? It was just a set, and now we define an operation on it. Let's call it dot. The dot operation takes two elements from a G quotient H, right? So it maps this to this element in G quotient H. This A star B is still an element of G, so of course this left coset is contained in G quotient H, right? So we can check that this operation forms a group structure on G quotient H. But here, the important thing is we picked a normal subgroup. We are not picking any subgroup. We are not picking some ordinary subgroup. Why we have to pick this normal subgroup? Because that is the only way to make this operation defined from G quotient H to, times this to this set. This is the only way to make this operation well-defined. What do I mean by that? We have seen that in our previous slides, these two elements are actually the same in Z, right? We pick this as Z over 3Z, let's say. These are both the same elements. The representing element changes only. So we should, if we have a well-defined map, we should expect, let's say we take this one and this one, these two elements, right? And this one, and let's make it 4 actually. We are still having this being equal to this one, this being equal to this one. So these two elements, actually the same element, should be mapped to the one element here. But in non-normal situations, this is what happens. We have this same element, but this is mapped to different elements when we change this representing elements. But this is not okay. This is not a well-defined map then. I mean, since here we have an abelian group Z, every subgroup is already normal. So this is, in this example, of course, these are going to be mapped to the same element. But I'm just trying to give you an example where things could go wrong in some ordinary subgroup. Okay. So normality here is needed to make sure this binary operation well-defined. Okay, next we form these group homomorphisms. Okay, we started with the set, we defined the operation on it, an operation, and then we have a richer structure now, right? And algebraic structure. So we can't just leave the maps as ordinary functions. We have to make them richer too. And the way we make them richer is we add this condition here. So this function should be preserving the group structure, and this is the way it does it. We have this A star B in the first group, and it is mapped to FA dot FB. The operation on H could be different, right? But this is the story. This element gets mapped to this here. So if this condition is satisfied, we have a homomorphism, not just an ordinary function, but a homomorphism now. A group homomorphism, because if you have modules, if we make sure that it preserves every operation on it, scalar multiplication and the operation of the module, is going to be a module homomorphism and ring homomorphism and so on. This one is group homomorphism. Intuitively, homomorphisms in general are the functions which preserve the algebraic structure. Since we are working on groups here, of course, this is going to be called a group structure. And again, we have some fancy names for one-to-one, let's not say functions, homomorphisms now this time. Injective homomorphism is called a monomorphism. A surjective one is called epimorphism. And if it is both injective and surjective, in other words, bijective, then we have an isomorphism. So two things about this. Actually, there are more than two things, but these two are going to be enough for now. The identity map is getting the identity element, of G is getting mapped to the identity element of H under this homomorphism. And the inverse of an element is mapped to the inverse of its image. Yeah, right? It's safe to say that, yeah. So these two conditions are satisfied under homomorphisms. So these homomorphisms gives us two interesting subgroups. First one is a subgroup of G, which is called a kernel F. We already know that the identity element of G is mapped to the identity element of H, but in some cases, actually in many cases, that is not the only element that is getting mapped to this identity. We have a bunch of elements here. Nonetheless, in both situations, we call this set of elements which gets mapped to the identity of H under F, kernel F. This is the name of this subgroup. And this subgroup has a very important property. It is normal in all cases. I mean, from G to H, you can define any kind of homomorphism, but still the kernel of that homomorphism will be a normal subgroup of G. And we can check that here, actually. We take any elements in this form, right? So we will see that under F, it is going to be mapped to the identity of H, because we have this from the homomorphism property. This A is getting mapped to the identity element because it's picked from the kernel of F. And again, we have Fg and Fg inverse here. So it is going to be end up being equal to identity of H. So this is a normal subgroup. Another subgroup is the image of a group homomorphism. So it's basically formed by the set of these elements in H, which has pre-images under F, let's say, yeah. So wherever this whole group is mapped, it's called the image of F. Image F is a subgroup, as we have been mentioning, but it is not necessarily normal. I mean, in some cases, it could be normal, where if H is an abelian group, of course, any subgroup is an abelian group. So in particular, image of F is going to be a normal subgroup too. But in other cases, image F might not be normal too. So it doesn't work like the kernel, actually. And we have two things here where kernel F being equal to 0 is equivalent to F being a monomorphism. We'll be using this in diagram chasing and all. And the image of F being equal to the whole group H is going to be, of course, equivalent to F being an epimorphism. Sorry, where did I go? Okay, here. Okay, so next we are going to be talking about free abelian groups, because again, in our example, it's going to be useful. So of course, it has a general formal definition, but here I'm going to try to build a free abelian group on the given set here, X, consisting of two elements, A and B. So we are going to take all linear combinations of these A and B. So basically, we are going to pick scalars, M, N, let's call them scalars. And we are going to take this linear combination, right? 2a plus 3b, I don't know, negative 1a plus 5b. Okay, the set consists of all linear combinations of these. And, okay, we have a set. Now we need an operation to make it into a group structure, right? So the operation star is defined as follows. So when we have two elements from this set Gx, the operation maps this, elements to m plus pa and m plus qb. So this operation gives us a group structure on Gx, and the identity is 0a, 0b plus 0b, sorry, and the inverse is defined like this, and element ma and b is negative ma, negative and b. Of course, it's going to be giving this identity element. So this Gx is called a free abelian group having the basis x. Again, as I said, this has a formal general definition, but we just formed this with these two elements. We can form it with one element, three elements, right? So here, the thing, one more thing is the number of generators is called the rank of this free abelian group. In this example, the rank is going to be 2 because the cardinality of X is 2. X has 2 elements. Okay. So we are done with the ingredients parts. So groups, subgroups, normal subgroups, quotient groups, which is very important because homology is defined as a quotient group. And now let's start forming our chain complexes. Sorry. So a chain complex C star D star is a sequence of abelian groups. C star, so we are adding a bunch of abelian groups here, right? And homomorphisms connecting these, dn plus 1, dn, and so on. But okay, this is how the structure looks like. But this structure has to be satisfying this condition. At each step, at Cn plus 1, Cn, and all, we should have the kernel of the a homomorphism should be including the image of the preceding homomorphism. At each step, we should be having this condition satisfied. Then we call this a chain complex. This is an equivalent condition to dn composition dn plus 1 being the zero map. Here's a figure. Here, let's say we are, zooming in this C3, C2, C1 situation and trying to see what is happening at C2. Okay, we have the abelian group C2, and the kernel of this D2, of course, is a subgroup of this one, so included in this one. And the image of D3 is again a subgroup of this group, right? And since we have a chain complex here, this condition is satisfied. So image D3 is contained in kernel D2. All right, and as we can see, this is the image of D3, right? But D2 is mapping all these elements here to the zero element. So in particular, of course, D2 is going to be mapping this little set here to the zero element. So if we take the composition D2 with D3, of course, D2, D3 should be giving us the zero. I mean, it takes any element of C3 to, as you can see, the zero element here. So that's why these two conditions are equivalent. If one of these is satisfied, then we have a chain complex. Here's an example. I picked some quotient groups Z over 16Z, Z over 8Z, and 4Z and all. And the maps are multiplication with 8 here, and 4 here, and 2 here. And the result will be modulo 4, 8, and so on, right? So in this case, we have these elements here. Here, 1 is actually denoting 1 plus 8Z. Okay, so I use this short, notation here, let's say, for the elements in Z over 8Z. So we have this multiplication by 2 here, right? So any multiples of 2 here, again, multiplied by 2 will be getting mapped to the zero element in Z over 4Z, of course. And the odd ones is going to be mapped to 2, right? Okay, so under this homomorphism, if we multiply the elements here, 4 times 0 is 0, 4 times 1 is 4, and if we move on, 4 times 3 is again 12, 4, right? All the elements are getting mapped to either to 0 if they are even, or to 4 if they are odd. So the image of this homomorphism consists of 0 and 4, but the kernel of next one consists of 0, 2, 4, 6, so it's included in this one. So our condition is satisfied here at each step, actually, but in particular, we should see it in this step. Okay, this is an example of a chain complex. Now we have exact sequences. These are special kind of chain complexes where we make this condition a little bit stronger, right? So again, we have this same structure, abelian groups and the homomorphisms connecting them. And in addition, we have this image being equal to this kernel. So at every step, the kernel of the homomorphism should be equal to the image of the preceding homomorphism. If we have this stronger condition satisfied, then we have an exact sequence. And when we have exact sequences, our figure becomes this one, right? So the image of D3 is going to be equal to kernel D2, which is represented by this green, set here. And it's going to be mapped to 0 element here. So this is what our figure now turns into. Again, we have an example. We have a very simple, basic example here, actually. We have, again, these quotient groups Z over 4Z at each step, and the homomorphism is the same at each step, multiplication by 2. So 2, maps all these elements here either to 0 or 2. And the kernel is also 0 and 2, because when we multiply it with 2, we fold in this 0 here. So the image and the kernel is same at each step. So this is an example of an exact sequence. Now, before defining the maps between these chain complexes, we have a new algebraic structure now, right? Which is a chain complex, and we have another one. What is, how can we make the relation between these two? We make these by chain maps, but before that, let's talk about commutativity of a diagram. When we have a triangle diagram like this, or a square diagram like this, in both cases, the story is the same. okay, I'm starting from A, I'm gonna land on C, but it doesn't matter which way I pick, this way or this way, I should be landing on the same elements for each element of the domain. So G composed with FA should be equal to the HA for all A in A, right? I pick an element here, no matter what. If I travel through this way or this way, I should be landing on the same element. The story is the same for the square diagram. If I pick this way, G composed with F, or this way, K composed with H, they should be giving me the same element. This is the commutativity of a diagram. So now we are ready to define these chain maps. Suppose we have here C star prime, D star prime actually, because this is representing all these homomorphisms here, and we should have another star here, okay? These two are the chain maps and the chain complexes. The chain map between them consists of sequence of homomorphisms, right? These homomorphisms, Fn plus 1, Fn, and Fn minus 1, which is defined, Fn is defined from Cn prime to Cn. So this sequence here, sequence of these homomorphisms altogether is called a chain map from the chain complex C star prime to C star. But under this condition, of course, if this condition is satisfied, we need this commutativity where the following diagram commutes. So here, in this diagram, the commutativity will mean Fn minus 1 composed with Dn prime, right, will be equal to Dn composed with Fn. At each step, we need to have this commutativity. And if that condition is satisfied, we call this a chain map. Okay, so we have these structures, we have these maps between them. Now, one last thing, the short exact sequence, actually this is a special kind of an exact sequence where the specialty is it starts from 0 and ends up with 0, and we have these 3 abelian groups here, right? So the exactness of this sequence gives us some informations. First of all, of course, this is satisfied. At each step, we should be having the image of the preceding homomorphism should be equal to the kernel of the next one, right? So this is just, straightforward. And the next one is kernel F should be 0. Why? Because, we have just trivial group here, 0, right? And the image of this map, this 0 map or inclusion map, no matter what, the image will be the 0 here. The 0 element is mapped to the 0 element, but that is all. We don't have any other elements. So if kernel F is equal to this image, then kernel F also should be 0, right? So this implies, as we mentioned earlier, this implies this F is a monomorphism. And next one here, again, we have a map here where all the elements of C is mapped to the 0 elements, right? So the kernel of this homomorphism is whole C. If it is equal to the image, of course it is because we are talking about exact sequences, the exactness of the sequence gives us that image of the G is from here to here, right? The image of G has to be equal to the whole group C again. And this implies that G is an epimorphism. So when we have a short exact sequence, these 3 are satisfied. Here we have an example of a short exact sequence. We pick a group G and then normal subgroup of G because we are forming this quotient group here, right? And the maps are defined as, this is just an inclusion map. Since A is included in G, we can take any element of A to itself, and this is a homomorphism. And the next one is defined as, we pick any element G and take it to its left coset, right? I use the addition notation here. I could use also this one, the left coset. So this is a natural projection. And this, this sequence is exact. We need to see 3 things here. Kernel I should be equal to 0, image I should be equal to kernel P, and image P has to be equal to the whole group G quotient H, right? So let's start with the first one here. So we pick an element, an arbitrary element from kernel I, and we are going to try to see this element is equal to the 0. if we pick this element from the kernel of I, then IA should be, equal to the 0 of the next group, right? But IA is also equal to 0. Sorry, A. So A has to be equal to 0. Thus, the kernel consists of just the 0 element. Okay, this is checked. And next, when we are trying to show the equality of two sets, we show that image I is contained in kernel P, and if also kernel P is contained in image I, we can say that these sets are equal, right? So this is what I am trying to do here. I pick an element from image I, and I am going to try to see that this element is in kernel P also. So if G is in this image of I, then there should be an element of A, right, which is getting mapped to this G under I. But I know that IA takes A to A, so this A should be equal to the G. I mean, this is just pretty straightforward, and maybe, okay. So G is an element of A too, because it's equal to the A, right? An element of A. So PG, now I'm taking this element G and trying to see where it lands on, it lands on G plus A. Since G is a member of A from here, we have that G plus A is equal to A. Remember, we had X H equal to H when X is a member of H. The same story here, G is a member of A. That's why G plus A is equal to A, which is the identity of this group G over A, right? 0 plus A is the identity of this group. We can denote it as A also. So since this is the identity, since this element is getting mapped to the identity of the second group, then this element should be a member of kernel of P, right? Then this implies that image I is contained in kernel P. So the first part is okay. For the next part, we take an element from the kernel P this time, and we are going to try to see it's an element of this image I. Okay, if this element is in kernel P, then it should be getting mapped to this identity A, right? So H plus A should be equal to A, but this will imply, sorry, not P, this is H. Why? Okay, there are some mistakes here. So these are H. If H plus A is equal to A, then H should be an element of A. Then H is, equal to the IH. Then this is an element of image I. Okay, these are H's. So which will imply kernel P is contained in image I, and overall these two sets are the same. Okay, the second condition is checked too. The next one is pretty straightforward. We pick an element G plus A from this quotient group, and of course this guarantees the existence of this element. So we have an element of G which is getting mapped to this element. So of course we have the image P is equal to G over A, because we have this inclusion, and the other inclusion is always guaranteed, right? Image of this P always is a subset of this subgroup of G over H. Sorry, A. Okay, so this given sequence is a short exact sequence. It's an example of short exact sequence. Now we move to, how's our time? Okay, we are doing okay. We move to our first puzzle. So we have a commutative diagram with exact rows. Now we know what the commutativity means. Means we have, these squares are commutative, and we have exact rows. We know what is the exactness of a short exact sequence is. And in this case, let us show that if F and H are monomorphisms, these two, then the middle one, the G, has to be a monomorphism also. So here we take a look at our tools first. What can we use, right? We make some observations. And first observation is based on the commutativity of this diagram. So if this one is commutative here, we know that this way and this way should be the same. So H composed with V should be equal to, beta composed with G. And the commutativity of this one gives G composed with U is equal to alpha composed with F, right? Okay, these two informations are coming from the commutativity. And next, we have this exactness of these rows. And from here, we know what a short exact sequence, right? We have all these satisfied. Kernel U is 0, image U is equal to kernel V, and image V is C. And the next row from the exactness of this row. So, okay, we have these informations too. Next, we are also given that F and H are monomorphisms, which means kernel F and kernel H are going to be 0. These are the informations given us. And now we need to show that G is also a monomorphism. To show that G is a monomorphism, it's enough to show that its kernel is 0, right? We have been seeing why these are equivalent. And we pick a random element B from the kernel G. And what we do is we try to show that it is equal to the identity of B, which is denoted by 0 of B, right? So we are at B now because we are picking this element from kernel G, and the kernel G is a subset of B. All right, so since we are picking this element from the kernel of G, GB has to be getting mapped to the 0 element. So if we apply this, beta to this element 2, then we should be landing on 0, because G maps B to 0, and any homomorphism maps the 0 element to 0 element. So B composed with GB is equal to 0. But if we use the commutativity of this diagram here, we know that H composed with B is equal to beta composed with G. Then this element should be getting mapped to the 0 under this H composed with B, right? But we know that from here, we know that kernel H is 0, okay? So if kernel H is 0, this VB has to be 0, okay? And this means if this V map is getting this, mapping this B to, okay, if B is mapping this B to the 0 element, then this B has to be an element of kernel V, right? All right, so far we were here at B, and we used this blue part here. We used the commutativity of this part. Now we are going to be using this exactness here. We know that kernel V is equal to image U, right? So if we have this B as an element of kernel B, this means that B is also an element of image U. In other words, there must be some elements of A which is getting mapped to B under this homomorphism U, right? So we are using this part right now. And we are moving from B to A now. We are at A. Okay, move on. Again, by commutativity of this square right now, if we apply alpha composed with F to these elements, it is going to be equal to G composed with UA, right? Okay, from commutativity, we know that. And this is equal to G UA, sorry, we can write it in this way. And this means UA is equal to B here, right? UA is equal to B, but we know from the start that G maps this UA to, this B to 0, because this B was an element of kernel G. Okay, then this means that alpha composed with FA is going to be equal to 0, 2. So alpha FA is 0. Since kernel alpha is 0, how do we know that? From the exactness of this part, right? Kernel alpha is equal to image of this homomorphism. That's why that is 0. Then this element FA should be 0. And since we have kernel F is also 0, why? Because here F is a monomorphism, and that's why its kernel is 0. We are using that information. Then this element A has to be 0. All right. So we know that B is equal to UA. U is a homomorphism, and U takes the identity to identity. Then this B element has to be equal to 0. So kernel G is equal to 0 because we picked a random element from there and we saw that this is equal to 0. So thus, this G is a monomorphism. All right, this is an example of a puzzle, an example of a diagram chasing. All right, so again, let's see. We are given this commutativity, the exactness, and we are given these these two are monomorphisms, and we show that G is a monomorphism, right? We use these tools. We use nothing but these, information that's given to us. Any question here, maybe, about the diagram chasing, about the methods we use? Okay. If we move on, we can see that this is satisfied too. I mean, if we pick F and H as epimorphisms, then the intermediate one, G, has to be an epimorphism. And we have this condition for monomorphisms. We have it for epimorphisms. And if we combine these two, of course, we will have this isomorphism situation. If F and H are isomorphisms, then the middle one, G, has to be an isomorphism too. We can show these two by following the same method, by following the information that is given to us. So another example, actually this one is called the short 5 lemma, and this is the long version of it. We have A1 to A5, this abelian group, B1 to B5. We have commutative diagram again, so each of these squares are commutative, right? And the exactness of the rows. Again, image of F1 is equal to kernel of F2, or image of F2 is equal to the kernel of F3, and so on. And from the commutativity, for example, H5 composed with F4 is equal to G4 composed with H4. And in this situation, if also in addition, H1 is an epimorphism, which is represented by this red color here, and H2 and H4 are monomorphisms, which is represented by these blue colors, then H3, this one, has to be a monomorphism. And if H5 is monomorphism this time, and if these two are epimorphisms, then the middle one, the H3, has to be an epimorphism. Okay, this is called the 5 lemma. And again, if we combine these two, if H1 is epimorphism, H5 is monomorphism, and H2 and H4 are isomorphisms, of course, now we will have H3 as isomorphism. We could use this one to obtain the short one. We could replace this A1 with 0, B1 with 0, and this one 0, and this one 0. And these are going to be the 0 maps from here to here, right? And 0 map from the 0 group or trivial group to trivial group will be both injective and surjective, both an epimorphism and monomorphism. And these conditions are going to be the same thing with the short 5 lemma then. Okay, this was another example of a puzzle. And okay, we have these chain complexes, chain maps, and we have an algebraic structure here. But I mean, how is this being useful? Okay, it's beautiful, and this game is fun to me actually. After you get used to its methods, it becomes fun after some point. And okay, but how can we use them? The answer is, one of the answers actually is homology groups. We can check the homology of these chain complexes, and in some cases it gives us some meaningful information about some spaces and all. And how is it done? Okay, the homology group is defined as follows. So we take a chain complex, right? This is our structure, and we have this, kernel including image stuff. The condition is satisfied, and the nth homology group of this chain complex is defined as kernel dn, quotient, image dn plus 1. All right, we are forming a quotient group here again, but we know that in general, this image is not normal. So maybe in some cases it will be, meaningless to talk about this, but no. Remember, we formed these chain complexes using abelian groups. So each of these Cn's are abelian groups for every n. So this means we have normal subgroups here. Image is always a normal subgroup. Then we are safe to form this quotient group in any cases when we have a chain complex. Okay, excuse me. So we have an example here, just a short basic one. we have this complex. I don't know what happens in this side, but this side, but I'm just zooming in to this part here to show an example of a homology group. The map D2 is multiplication by 4 map, and D1 is, of course, the 0 map. It takes any element of Z to the 0. And in this case, the homology H1X is kernel D1 over image D2, yeah. The kernel D1 is, as we said, we have this Z here, but it is all getting mapped to the 0 element here by D1, right? Sorry. So whole Z is the, kernel of this D1. And the image D2 is, of course, when you take a look at here, if you multiply any integer by 4 here, we have 4Z, right? The all integer multiples of 4. So we have 4Z, and then the homology group of X, first homology group in this case, will be Z quotient 4Z, which is isomorphic to Z4. It's just a basic example. But when we take some random abelian groups, we could plug here Z's, Q, R, any matrix, group, or some other composition groups. We can, plug anything here as long as we have this image containing kernel property satisfied. We can form any kind of chain complex, and then we can compute this homology for each of them. But what is the use of that? What is the meaning in a general case? So if we pick random abelian groups, maybe it might not be that meaningful. But if we form these abelian groups, if we obtain these abelian groups from the same source, let's say we have some kind of space, and each abelian group, Cn plus 1, Cn, and Cn minus 1, is representing a part of this whole object, then this chain complex becomes meaningful, a little bit more, sorry, I can't say that, a little bit more meaningful. And the homology, again, gives us some information about this space in this case. So, okay, but how do we do that? How do we form these, abelian groups? Let's give some, information before we tell how we do that. So we have these simplexes. Maybe some of you are already, familiar with these simplexes, but these have formal definitions in general for, higher dimensions too. But I'm trying to keep things simple here, so I'm just gonna tell what is 0 simplex is. It's just basically a point, right? The 1 simplex is we take 2 distinct points and the line segment between them. And the 2 simplex is, again, we are picking 3 points. Of course, they shouldn't be lying on the same, line, right? So we take the interior 2 and we form the 2 simplexes and 3 simplexes and so on. As I mentioned, these all have formal definitions, but I just don't want to, dive deep in the formal definitions. But of course, they are useful for higher dimensions. And we have this orientation thing, which is going to be very useful in homology calculation. It is like an ordering. If we, write A, B, so what we mean is we give a direction to this line, and we mean this direction is from A to B. If we write BA, this direction is from B to A, okay? So if we give an orientation to a 2 simplex, it is either counterclockwise or clockwise. And, in this case, if this is counterclockwise, so we have A, B, C, right? And so on. This is the orientation on these simplexes. So what are these simplexes good for? In topology, we have these spaces, right? For example, D2, for example, S1, the disk, or the circle. So in topology, we are kind of allowed to do some deformations. We think of this disk as made from rubber, and we can deform it as long as we don't tear it apart or glue some sides of it. We are allowed to do some deformations, and one of these is we can just apply pressure from the sides and from the bottom, and we can just obtain this 2 simplex here, right? This is a 2 simplex. The interior is included too. But in the circle case, we can do the same deformation again from the sides and bottom. But now we have again a triangle here. but this is not a two simplex because the interior is not included. So as you can see, for a two simplex, we should be having the interior too, but we don't have it here. Instead, this is a kind of a union of one simplexes, right? This is a one simplex, this is a one simplex, and this one. So we take these one simplexes and glue them, and we form this, object, right? So this is why we need some a little bit more complex structures. Just these simplexes are not enough to represent all spaces, right? So that's why we need these simplicial complexes. But here we, glue these one simplices like this. In general, we need a nice way of gluing. What do I mean by nice way of gluing? Again, I'm not going to go into details, but we should be, if we have this two simplices glued like this, the intersection is a one simplex here, right? And it is a face. I didn't mention about the face definition, but this two simplices, simplex has these three one simplices here and three zero simplices here, right? So that is, let's call these faces of this one. So this intersection is the face of this simplex and this simplex at the same time. This is the main rule. Another one is when we have a simplex in a simplicial complex, all faces should be included in this one, but this is where usually the problem, occurs. We have this intersection here. Okay, this is not a face of this simplex. This faces of this simplex are these, and this one, right? So this part, let's change the color. This blue part is not a face of this one. So this is not a nice way of gluing. This also is not a nice way of gluing, but these are okay. So we glue these simplexes together and we form these simplicial complexes. And these are useful, as we can see here in this example, to represent other topological spaces too. So we can, for example, represent torus with these union of this gluing of two simplexes, and Mobius band as this like this, and the Klein bundle like this. So, okay, we can represent these spaces with simplicial complexes. And if we had a way of obtaining these chain complexes from these simplicial complexes and computing their homology, maybe it could give us some information about these topological spaces, right? And actually we have a way, and it is defined through this free abelian group notion. So for n is greater than or equal to 0, C and X is the free abelian group generated by n simplexes in X. So for n equals 0, we have these, in our example, we have these 0 simplexes here, right? A, B, C, and D. So this free abelian group is generated by these 4 generators. Okay, one dimension higher, we have this A, B, B, C, A, C, D line segments here, right? The one simplexes, and this C1X is generated, a free abelian group generated by these one simplexes. And the second one, sorry, it's C2X is generated by 2 simplexes, which is we only have A, B, C. Okay, we have B, C, D as a triangle here, but since the interior is not included, it's not a 2 simplex. That's why we can't have that one here. All right, so that is how we form these abelian groups. Okay, and for n is greater than or equal to 3, we don't have any 3 simplexes here or 4 simplexes and so on. That's why these are just the trivial groups. So our picture is like this. We have these zeros here, bunch of zeros in other dimensions, and C2X is non-trivial, C1X is non-trivial, and this one is non-trivial. And okay, we obtain these, abelian groups, but also we should define these maps between them, the homomorphisms, because we need to make sure that the condition is satisfied, right? To have a chain complex. These maps in this particular case are called boundary maps because, intuitively they are taking any simplex for a 2 simplex, for example. The boundary of this 2 simplex is the outer part of this triangle, right? So it takes it to its image. Let's say the orientation is made like this. Okay, so we will have AB, this one here, and BC, this one, and minus AC, because this orientation from A to C, but this orientation from going from this side, so we should move the opposite side. That's why this is negative. Okay, this is the boundary of these two syntax. And for a one syntax here, D1 takes it to its boundary again, but in this case, the boundary of this syntax is these two zero syntaxes, right? And so if the orientation is from here to here, since we write AB, of course it is, then the result is B minus A. All right, this is how a boundary map works. Again, as I mentioned in the beginning, there are formal definitions for these because we need those to generalize these ideas to higher dimensions. But I'm just trying to give you some basic examples to maybe have make you have a idea about the essence of the stuff. So let's do a computation here. We are going to compute H1X, which is kernel D1 over image D2. Kernel D1 over image D2, right? So for the kernel, to determine the kernel, if we pick any elements from this combination, right, these P1, P2, and P5 are integers. So we are taking a linear combination of these generators. And if this element is picked from D1, D1 should be mapping this sum to 0, right? So since D1 is a homomorphism, we can rewrite it as this way. We can observe what happens at each generator and the sum, we can take the sum. So D1 operates on AB as B minus A, as we have seen, this is a boundary operator. And here we will have C minus B, C minus A, and all these. This is going to be equal to 0. And if we rewrite this, for A, we have this coefficient. And for B, we have this coefficient and this. So if to be able to have 0 in this sum, the 0 element is denoted by like this, right? B, 0B, 0C, and so on. So each coefficient should be 0. Then we have this system of equations for the coefficients. And if we solve this system of equations, these probably from linear algebra, we can use this reducing system here, and we will see that P3 and P5 are going to be free variables, and we can represent the others with respect to these. So overall, we will have these generators, and the kernel will be generated by, so P1 is -1, I can pick that, and P2 is -1, and P3 is 1, and all the others are 0. So this will give me this element. And next for this one, if I pick P1, 0, P2, -1, and all, I will obtain this element. So the kernel of this D1 is generated by these two. So in our example, we had something like this, right? A, B, C, and D, like this. So let's see. Negative AB, let's use a different color. A, B, so like this. Negative B, C, plus AC. This is just abelian, so I can change the order. Plus AC and this one. So we have a cycle here, as you can see. And this one is negative BC, so another color. And so this is the, plus BD and negative BC from BC, or of course, this should be this side, right? BC from B to C and the negative. So this the opposite side, and here we have another cycle. So these two elements actually represent these cycles here, these loops, let's say. Okay, this is not the only loop we have. I mean, if we take this one, right, the other one, this is still a loop. I can start at A and loop around here. But this loop is actually a linear combination of these two loops. Now, when you take the negative of this, what's going to be happening? BC plus CD minus BD, right? So if we add it to this one, these BCs are going to cancel out, and what is left will be negative AB plus AC, and it will give you this BCD, this loop here. So this loop is generated by these two. Okay, we have that too. So, buyurun.
Araya giriyorum, pardon. Son 5 dakikamız kaldı da hatırlatmak istedim.
Tamam, biraz daha hızlanayım o zaman. Okay, so the kernel is, generated by these two elements. Aslında bayağı da slide'ımız kaldı. These two elements, and next one, the image of D2. This D2 maps this two simplex to its boundary, as we mentioned, right? So this is the only generator of this C2. Then I can just keep track of this generator under this homomorphism, and this will give any the idea about any elements that is generated by this one, because it's a homomorphism. So this element is getting mapped to this one, and image D2 will be, generated by this element. And if we form this quotient group now, we have a group that is formed by these two generators, quotient, a group formed by this generator. But if you look closely, if you multiply this with -1, you will have this exact loop here, right? So this generator, whatever it's generated by this, will be vanishing in this one. It is already an element of this one. And as you remember again, xh is equal to h when we have this x as an element of this h, right? So this is an element of this subgroup here. Then if we form the quotient, this is going to be mapped to the 0. So we are only going to be left with this element plus image D2. So we have one generator for this h1x. So in general, the rank of h1x is exact number of one-dimensional holes in h1. And in this setup, the nth homology group detects the number of n-dimensional holes in the space for n is greater than 0. And for the 0 case, it only detects the connected components in the space. So this is actually what's going on. Again, we have this D1. This D1 is mapping anything generated by this triangle and this triangle to 0. And the two simplex here is getting mapped to this ABC, the boundary of it, right? The image of this D2 is, this triangle. So if we form the quotient group, what we are doing is we have this information from the kernel. There are two possible holes in your space. That's what this kernel was telling me. And the image is telling me that, wait, one of these is a boundary of this simplex. That's why the interior is actually filled, right? And the homology is kind of a way of combining these two informations and give us a final information that we only have one hole in our space, which is the case here. This one is filled and this one is empty. So we have just one-dimensional hole in our space. So as you can see, if we form these chain complexes from just one object, if we form these if we are building groups from one object, the homology is actually have a meaning like this in this setup. And yeah, that is all I want to say for today. Birazcık da süreyi aşmışım. These are the references, and thank you for all for coming here and listening to me.
Çok teşekkürler hocam konuşmanız için.
Ben teşekkür ederim.
Arkadaşlar sorusu olanlar varsa isterseniz başka bir şekilde hocamızın mail adresiyle ya da iletişime geçelim. Çünkü bir sonraki konuşma da burada olacak hocam. Hocamızı
Tamamdır.
bekletiyoruz.
Tamamdır.
İsterseniz mail adresinizi chat kısmına yazabilirsiniz.
Tamam,
ya da
o da olur.
söyleyebilirsiniz.
Hamdi Kayaslan, direkt ismim soyisim @it.edu.tr. Şeyde yazabilirim ama chat kısmına da yazabilirim.
Tamam. Tekrardan çok teşekkür ederim hocam.
Rica ederim. İyi günler herkese.
İyi günler.